Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. So we proceed to the last part of chapter 1, okay, which is the virial equation and power equation. So uh, as we go through previously, basically you have learned how to use the table and the based on the data that you have in hand. Okay, so proceed with that. Any equation that relates measured properties. So in this case, we call it as the ideal gas equation of state. Like you have covered this one right during thermodynamics, whereby PV equals to RT, and whereby the ideal gas has low pressure and high temperature, with the universal gas constant, for example, are at 8.314 joule per mole Kelvin. And you are aware that there are several types of universal gas constant according to the unit given at the back of it. So just beware. And there are various forms of equation of state depending on the form of the equation, which are categorized as cubic or virial equation of state. And there's a question for you, so you can drop your comment in the comment section down below. Why ideal gas equation of state is not sufficient alone to describe the substance? Okay, drop down your comment. Yeah. Okay, next one. So for the variation, we start with the equation of state. Basically, the equation of state occurs in a single phase region, whereby for the regions where a single phase exists, the relation connection between PV, which are the thermodynamic properties, may be expressed by P function of pressure, volume, and temperature equals to zero. Meaning, an equation of state exists relating to pressure, molar or specific volume, and temperature for any homogeneous fluid in equilibrium state. It can be pressure to the function of temperature and density, and enthalpy to the pressure to the function of temperature and volume, and so on. So there are several and different types of interpretation, as long as it can relate to the at least two thermodynamic property of one parameter that you want to measure. Okay, for example, if V is considered a function of temperature and P pressure volume, VTP, thus dV equals to this equation below. And then, however, the most common choice in thermodynamic is pressure equals to the function of temperature and volume, whereby if you look through, this is the form of ideal gas law. All right, so because we have T and V, so it says that the simplest equation of state is the ideal gas law, which we have learned previously in your thermodynamics. So in this case, pressure to the function of T and V equals to RT per V. So despite the V is 1 over V, because the PV equals RT, uh, is that's why it is called as the simplest, because it's just straightforward, right? And then this is Van der Waals. So he is the person that introduced the addition some terms next to the ideal gas, because we know that the simplest is PV equals to RT, or PV equals to nRT, when ideal gas law is not valid, which accounts for the size of molecules that interact and the specific interaction whereby there are attractive forces. So it is called a non-ideal or real gases. Okay, so for this situation, PV equals to ZRT. So we can see that Van der Waals has introduced another definition, which is P equals to RT per V minus B minus A per V to the power of 2. So so we can revise it as Van der Waals equation of state, cubic in volume, PV to the power of 3, as follows to the equation equals to 0. Okay. Okay, the first practical cubic equation of state was proposed by Van der Waals. Okay, so he is proposing this part instead of PV equals to RT. Yeah, and A and B are positive constants. So and when A and B equals to zero, ideal gas equation is recovered, right? So because this one is not valid due to this situation one and two. So this is non-ideal and real gases. Okay. The van der Waals equation of state cubic in V, one real root where if let's say the temperature is lower than the critical temperature, and the three real roots if the temperature is uh, higher than the critical temperature, and there are three real roots if the temperature is lower than critical temperature. And it is worth to note that the largest is the vapor phase and the smallest is the liquid phase. Where do we get values for A and B? Okay, one is data from PVT, which is from regression, and another one is corresponding states theory. Okay, for this equation A and B, right? Because this is the constant, and of course V we can know the value of VRT. So for A and B, so this is the equation 27 per 64 times RTC power of 2 per PC, and for B equals to RT critical 8 per 8 P critical. And how do you get the TC and PC? Right. So PC and VC actually you can get it from. I know actually I don't want to tell you yet, but I believe I hope that you really know. So I want to go through straight to the equation to the question. So given argon at 166 K, what pressure corresponds to a density of 5 kilomole per millimeter cube by using van der Waals equation of state? Okay, just a little hint because this is the van der Waals equation of state. So what are the things that we have to calculate? A, right? A and B. A and B. Sorry, this one A and B. Okay, basically you have the temperature and you have the volume, volumetric flow rate. Okay, so A and B you should find from TC and PC. So TC and PC you should find from this table. So any idea? Okay, the table you can get from actually from the book, from the textbook you can get from table A11 and table A12 because there's a value for TC over there, and for this one this is just example. So we can see here there's a temperature, critical point properties. So these are the properties for the critical point, so you can get the point from here. And yeah, you can refer to any kind of table as long as there's a value for critical temperature, because basically based on the phase diagram it should be fixed. Okay, so next one, moving on to the. Okay, make sure you give the answer down in the comment section below. Just a simple maths, right? But don't forget to change the unit. Okay, cubic equation of state. In reality, the behavior of substances deviates from the ideal gas law, and the intermolecular forces between molecules cause non-ideal gas behavior. And the example of intermolecular forces, for example, like the attractive forces come from dispersion, dipole-dipole attraction, induction, van der Waals, and hydrogen bonding. And the repulsive forces can be Lennard-Jones potential. So these are just example, just in case you want to know. But it's not that really that necessary. Okay, there are another various cubic equation of state. So we can see here for the van der Waals, it can. Okay, this is fixed. P equals to RT per V minus P, so you should add this one negative, no, minus this attribute. So there are several forms: Van der Waals, Rashleigh-Wong, Rashleigh-Wong Sof, and Peng Robinson. Oh, there's a Azan. I stop for a while.